This video explains the example of design the longitudinal reinforcement AST for the 500 mm by 1200 mm rectangular section shown. So these are rectangular sections. It has given M star equal to 300 kilonewton meters. Characteristic strength 25 megapascals, 30 millimeters cover to the R10 stirrups. Now this is an example for. Now this is an example for the design sections. If you this is the capacity of under reinforced rectangular section. In the previous video we have discussed this one, that if the capacity mu is known, then the area of tensile reinforcement may be found by using this equation. So we can substitute mu and we can find AST. So this is the design of reinforcement examples, just getting from previous example. Now we don't know what is the size of the bar, so the good starting point is to use N24 bars for the tensile reinforcement. So I use N24 bars here in the tensile reinforcement. Blue color one is the R10 stirrups, and we have 30 millimeter cover that is given here, and we have 10 millimeter stirrups, and we need to calculate this depth D. Now depth D is equal to 500 is given in the questions, that is 500 given in the questions. 500 minus 30, that is cover. Take away the diameter of this stirrup, then take away this 24, half of 24 divided by 2, that is given 448 millimeters. So it's basically measuring from the center of the reinforcement to the top of the fiber. So if I just draw it in the very simple format, this is the diameter, this is the stirrup, and this is the cover. So if I like to know this distance small d, it should be 30 millimeter, 10 millimeter, and this is 24 divided by 2. That's how it's measuring that total depth D. Take away these three parameters to give us 448 millimeters. Now we have given that applied moment is M star has equal to 5 MUO. So MUO equal to M star over 5, 300 over 0.85 is equal to 353 kilonewton. So we first calculate MUO capacity. Now these capacity factors phi u is given in table 2.22 towards AS3600. In this table 2.222 we have a capacity factor 0.85 for bending without axial tension and compressor for class and reinforcement. So we have taken 0.85. Now MUO equations that we discussed in the previous video, I can show it here again. So in the previous video we derived the equation for singly reinforced rectangular section MUO. These equations I copied here. Now in these equations we are using the unit Newton, millimeter, and say megapascals. So all the parameters are known. AS2 we need to find, MUO we know. We need to know alpha 2. Alpha 2 has equations. This one that is taken from clause 8.1.3 on page number 110 AS3600. On clause 8.1.3 we have a equation of alpha 2 equal to 0.85, take away 0.015 FC dash. So that is written here. Now FC dash is given 25 megapascals, that is given here 25 megapascals in the questions. We substitute that value is 0.8125. Please check the conditions. This is greater than 0.67, so alpha 2 is 0.8125. that is okay. It's given in the standard on the same clause. If you check it here, that alpha 2 value should be greater than 0.67. If this value is less than 0.67, we need to take 0.67. Now these equations we are substituting the value. N bar has a 500 megapascals yield strength. If you take the Rio data, later we are going to use it, and has a 500 plus rebars, that's what we use. So yield strength is 500 megapascals. It's not given in the questions, but when we assume N bars, it has a typically 500 megapascals yield strength. Depth D 448 millimeters. We calculated in the previous step. We calculated D 448 millimeters. 1 minus 0.5 alpha 2 we calculated 0.8125 times AST we need to find. B is 1200 given in the questions. B is 1200 millimeters times 448. We calculated that D in the previous step 448 millimeters times FSY yield strength of the reinforcement 500 and FC dash characteristic is 25 given in the questions. Now we are working in the MUO that we calculated here, 353 times by thousands times by 1000 to convert Newton millimeters. So this is in the Newton millimeters. Now this one is in Newton millimeters. 22400, we just do the multiplication, give us AST. 1 minus this simplification gives these numbers AST. Now 35300 10 to the power 6 to these values minus if you expand these brackets, that's give us these numbers. Now if you bring this one across, become plus, this one become minus, this one plus, equal to 0. Its typical equation is ax square. Let's say x is AST plus bx plus c equal to 0. So if you want to find the x value for that one, generally for our case is AST. So the AST can be used by this equation, quadratic equations, minus b plus or minus b square minus 4a 2a, where b is minus 224 times 10 to the power 3 plus or minus b square. B is 224 times 10 to the power 3 square minus 4 times a is 5.125 times that c value is 353 times 10 to the power 6 divided by 2a, which is 5.128. So that is the quadratic solution. Now if you simplify that one equations, then you will have a 224, the simplification of the square root give us 207 208, and 2 times 5.1 give us 10.256. Now it has two options, one is with plus, another one is minus. When you have plus, it gives us that big numbers, and another solution is 1637. We are focusing on this one, 1637. Now we have AST values 1637, so we have AST value 1637. We are taking these values. In that case, we just need to use these Rio data tables. In that Rio data tables, we have 1637 AST. In the Rio data tables, we should use 24 bars, and we need to get the number of bars which should have a area greater than 1637. So we have 1808, that is here. It has a number of bar is 4. So we use the 4 number of bar provided, and it has an area of 1800 millimeter square, and this taken from Rio data table. Now this one has a clear spacing between the bars. So if I like to calculate what is the distance between the one bar to the second bars, it is 1200. The total width is 1200 minus this is cover given in the questions, 2 times 30. We have two side covers. Take away this stirrup diameters, which is 10 millimeters, and take away this 4 times 24. We have this 24, and we have 3 gaps, 1 2 and 3. So divide by 3, it gives us this spacing 341. So this distance is 341 millimeters. Now in Australian standard 360028 clause 8.6.1b, on page number 131, on clause 8.61b, it has written the one sentence, center to center spacing of the bar near a tension phase of the beam shall not exceed 300 millimeters. So minimum spacing distance is 300 millimeters. So but we get 341, so it does not satisfy the condition of the Australian standard. So we need to select 6 and 20 bars, like we need to reduce the spacings bar, so we need to provide more bars here, so we can reduce that one. And if you go back to the Rio table again, and N20 bar and 6, it has a diameter of 1884 millimeters square. So that 1884 millimeters square that we adopted here, for which D is 450 millimeters. So as you know, in this one, if you substitute, instead of 24 we substitute 20, it gives us 450 millimeters. And if you repeat this again, definitely it will just repeat the whole process again for N20 bars, for small d 450 millimeters, it will give you the spacing less than 341, which satisfy this condition. Spacing should be less than 300, but should be greater than this dB and maximum aggregate size. Now for this one we need to do the two checks, one for the flux strength check, minimum flux strength check, and the ductility checks. We have N6, we have these bars 6 and 20 bars that we use. Now we need to make sure that it has enough ductility. There are two conditions we can check. The Ku value should be 0.36, that is the requirement of ductility. All the reinforcement should be less than the maximum reinforcements. We done the previous video on the calculation of the maximum reinforcement and reinforcement. Now Dn equations we saw in the previous video. In the previous video we found this calculation Dn 1 over alpha 2 gamma fsy fc dash ast and b. Now that equations we use it here. Alpha 2 0.8125 we calculated in the previous step, 0.8125 alpha 2. Gamma value we did not calculate, but that is coming from the standard 8.1.3. so in this one on the page number 110 on clause 8.1.3 we have a gamma value 0.97 should be greater than 0.67. so that is the gamma value. Now that is done here, and we just substitute fc dash is 25 because the fc dash value is given in the questions. Fc dash is 25 megapascals, so the gamma value is 0.9075. we just need to check the condition should be greater than 67. It is greater, so we adopt this value 0.9075. fsy for n bars and 20 bar is 500. fc dash 25 given in the questions, 25 megapascals, and this yield strength taken from the Rio bars because all the n bars has a 500 megapascals yield strength. AST 1844 we adopted N16 bars where we take this 6 and 60, we have 1884 millimeter square AST, so that is here. B is 1200, we have this 1200 millimeter B, so it gives us 42.6 millimeters Dn. Now Ku has an equation Dn on D, so 42.6 on D is 450. We done this one here where we have a D value of 450 millimeters. It's give us 0.095, so it satisfies the ductility condition is less than 0.36, so that is okay. Now we need to check the minimum fluxor capacity, so mu should be greater than 1.2 mcr, or the minimum reinforcement should be greater than minimum reinforcement. So cracking moment is FCTF times Z. Now this equation is given in the Australian standard to calculate FCTF. FCTF is given here 0.6 FC dash on the clause 3.1.13 on page number 44. So B D square on 6, so B is 1200 given in the questions. B is 1200, D is 500 square 6, so it's give us 150 times 10 to the power 6 Newton millimeters, converting to kilonewton meters. So it's 1.2 mcr is 1.2 times 150 gives us 150 kilonewton meter. MUO, so this MUO is 353 kilonewton meters, which is greater than 180, so that is okay. So minimum fluxor capacity is okay, so we can provide 6 and 20 bars. Thank you.